today I'm going to present my tech talk on 29th of October 2020 on the Alta battery and its applications in wind penetrated power systems. Uh, I'll be covering this in following the outline of the presentation would be carried by addressing the introduction, the objective, the aims and approach that I'll be incorporating, then the brief reviews, conclusion, followed up with the references. As far as the Ultra battery is concerned, Arjit sir, are you able to hear me? Arjit, hello?
Yes, sir. Yes, sir.
Okay, yeah, it was a pin
Okay.
drop silence. Okay, no problem. So, you are seeing the slides also, na? Ultra battery is basically an energy storage device. So, as far as the energy storage devices are concerned, so there are different types of energy storage devices available in the market. That is for high energy storage, and some of them include SMES, which previously in my previous tech talk we have seen, superconducting magnetic energy storage. Then we have flywheel, that is also incorporated. Then we have our supercapacitors. As far as the supercapacitors and SMES is concerned, there is no rotating part involved. Same is the case with ultra battery. And ultra battery was invented in the year 2007 at Australia with the Commonwealth Scientific and Industrial Research Organization, and then adopted in Japan by Furukawa Company. So, what is the advantage? So, different power systems or different applications require different ramping rates, time constants, and different power densities and energy densities. As far as the batteries are concerned, they are high in case of the energy density. Per unit weight, they'll provide you more energy, but they have less number of charge cycles. So, less number of cycles means they will have less lifespan. But ultra battery has an advantage of high power density as well as high energy density, like a supercapacitor. And in the power system, it has already been utilized with the Ecolt company, 3 megawatt installation in Pennsylvania in US for load leveling purposes. So more modern power systems have considered ultra battery for active power control. So what does exactly the ultra battery technology look like? So it comprises an lead acid cell and incorporated with an ultra capacitor. So you can see over this, the blue color is lead oxide, and there's a common separator and lead between. So it ultra battery combination gives you uh, an
Sir, sorry,
yeah,
sir. Sir,
yes, yes.
are you changing the screen? Because we are not able to see the.
Yeah, I'm changing the screen. Screen you are not able to see?
No, no, only the front slide we are seeing.
Okay, okay, okay. That's what I was asking. Okay, 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 sir. Well, I'll be again. Hmm, stop record. Okay, present now. Now you are able to see, sir.
Now it is correct, sir.
Okay, so outline of the presentation would be covered as in introduction, objective, aims and approach, results, conclusion, references. So as far as the ultra battery is concerned, it's an energy storage device which has a different ramping rates. And the advantage of ultra battery already, which I discussed, is it has the high power density of an battery as well as it has a high energy density, so that its life gets extended. It has millions of charge and discharge cycles. And ultra battery was introduced at CICERO, that is Commonwealth Scientific Industrial Research Organization, Australia. Then it was adopted in Japan for Kowa Company. And for power system, it is utilized for load leveling purposes. Like in Pennsylvania, they have 3 megawatt Ecolt battery that has been utilized for load leveling purposes. And modern power systems have considered ultra battery for high power, for active power control. Now this is the ultra battery terminology. It has a combination of a lead acid battery and an ultra capacitor. So it is a common carbon electrode and lead dioxide. So this is how an ultra battery looks like. So it has a lead acid cell plus ultra capacitor. That's why it gives a high power density as well as high energy density. So ultra battery comprises a combination of asymmetric supercapacitor inside a lead acid battery, which is separated by a common carbon electrolyte. So what is the advantage of the ultra battery is that as far as the other batteries are concerned, they have to be fully charged or charged to an optimal level. They don't work particularly well at times of partial state of charge. But in case of battery, you can operate the ultra battery and it is suitable even for operation at the PSOC, that is the partial state of charge operation. And it also helps to by reversing the value of the current. It works in both the directions by charging, discharging, or changing the rate of charging or discharging. And as compared to the other modules like super capacitor or SMES for that example, so that is super capacitor magnetic energy storage device, that SMES has a limitation. It works at a particular degree Celsius. You require a cooling arrangement, cooling things. So some SMES work at 4.2 Kelvin. Nowadays they have designed high temperature superconducting magnetic devices, but still they have limitations. Unlike those limitations, here we can utilize it in any normal temperature. As far as the other devices are concerned, like the supercapacitors also, they don't have the ramping rates that match the ultra battery. So it is like, because it is having the advantage of an battery as well as the supercapacitor, so it responds rapidly and can ramp much faster than any conventional generator, following the regulation control signal accurately and providing a better service to the system operator. Already previously also I have mentioned that at the grid scale, frequency regulation has been utilized by equal 3 megawatt installation within Pennsylvania, New Jersey interconnection. So how does the ultra battery chemistry look like, and the modeling of the ultra mathematical modeling of the ultra battery, and finally its interconnection with the power system. And we will see the response of the ultra battery when we are introducing a load disturbance, and how the ultra battery arrests the frequency and dampens, leads to a much faster power system restoration stability, as well as reducing the peak overshoot. So for by evacuation of charge and release of energy would be administered and characterized by circumstances like battery well-being, temperature, and limit of charge present inside the battery. The equation, that is, you have lead, you have sulfuric this acid plus your lead oxide. So you get this particular equation. And then the most of the ultra battery models are like in the literature which I have gone through, have not given preference to the state of charge or state of health. See the prevalence of state of charge, because it's very important. As the ultra battery we have discussed, it also works in the partial state of charge. So if it is 30%, 20% state of charge, it will work. But as far as the battery is concerned, it will not give its optimum performance. So there is a prevalence of state of charge characterization strategies in context of lead acid battery technologies. So methods concentrating on the state of health are less prevalent, mainly since being a quantitative qualitative, it's a qualitative measure, unlike the and what it does is, the battery will be, because of the sulfuric acid that is getting generated, there is a sulfation effect, and the normal batteries get deteriorated over a period of time. Whereas as far as the ultra battery, the lifespan gets tremendously increased, owing to its power density, as well as owing to the combination of the lead acid battery as well as the supercapacitor. So this is the electrical equivalent of the mechanical model. So herein we are seeing here Ri. So this is the current of the ultra battery. So you can see from here I will be deriving my matrix equation. So current I1 is going, so I3 and I4, so the same current I1 will come out of this, because I1 entered and I1 will all, because I3 and I4 same. See here I5 and I6. So same, I1 is equal to I5 plus I6, and I1 is equal to I3 plus I4. So similarly here also we can see the current I is equal to I1 plus I2. So from here we will see, we will take that for our state space modeling. what I will be doing is that capacitor voltage I will take one of the model, and the inductor current I will be following. So here I am not having inductor current, I am having a RC module of the ultra battery. So this figure is details a helpful electrical similarity of the unpredictable synthetic responses of the cell. So the different parameters of the model are Ri, that is here Ri, it denotes your R current, denotes the dominant arrangement of cell resistance. By it, the lumped resistance for various interconnections inside the cell is assigned. So basically, this model is a modification of a Randall's equivalent circuit. So the Randall's from that equivalent circuit, we have resulted into this particular chemistry, and have designed the RC model. And then you have CS here. This is the bulk capacitance. CS delineates the two-fold layer capacitance, or this is also called the and came about by detachment of charges at the interlink limits of the electrolyte and the cell plate. And we have here the transfer resistance RT, and it presents the charge exchange resistance. Likewise, this methodology of charge exchange gives what might as well be called the natural speed reflected by responses bring about the charge exchange. What happens is that this is helping in the this ramping rates and other charge exchanges. So it also is very vital. And then you have, this is your C surface, and then you have CB, that is your C bulk. It mirrors the major capacitive component displayed inside the cell. So this is your C bulk, whatever major capacitive component is represented by your C bulk inside the cell. And then we finally have this R discharge, which we denote the release resistance inside, which is given by load authorized upon mass capacitive component. And its range is around 10 kilo ohm for a dynamic cell. So to make a state space model, what we have assumed is that let x1 be the voltage across CS. So x1 with the voltage here, x1 is the voltage across CS, and x2 voltage across CB, x2 is the voltage across CB, and x3 is the voltage across CX. So what we will do is that the type of the equation, see from the circuit already I mentioned over here, from this circuit I1 would be equal to I3 plus I4. Same I1 is going, this is equal to I5 plus I6. So from this equation, simple KCL I am applying. I1 is equal to I3 plus I4, and I1 is equal to I5 plus I6. Now this I3 is here, so this I3 is here, so I can express this I3 in terms of my capacitance. So in terms of my capacitance, when I'm expressing it, so I can write my I1 is equal to I3 plus I4. So I3 would be x1 by RT, and I4 would be CS into x1 dash, because dx by dt, dv by c, dv by dt is equal to I4. See here, this, sorry. So C dv by dt would be I4, and similarly here you have RT. So RT would be the voltage divided by the current, x by RT, whereas here it would be Cx into dv by dt, that is your x1. So here I have written, so this is I1 is equal to x1 RT Cx x1 dash, where my x1 is the voltage across CS, and that voltage I have taken dv by dt, and here v by RT. Similarly, I can write I1 is equal to x2 into RD, because from this I5 and I6 I can write here I5 and I6. So I5 again, see I6 would be the voltage across, this is x2 by RD, and this would be CB into d by dt of x2 dash. So that is CB into x2 dash plus this voltage would be equal to x2 by RD for I6. So same equation here, x2 by RD plus CB x2 dash. So and similarly you have directly also you can write your I2 is equal to Cx into x3 dash. Your I2 here, I2, because you have Cx into x3 dash, or you can also write V by Rx. So I have taken these equations, and from these equations I have written your entire voltage would be equal to considering the voltage or drop across current, and these three voltages are there, I1 into R1 plus X1 plus X2, and in V I2 Rx plus X3. So what I do is I am putting 2 in 5, I get this equation Putting equation 2 in equation 5, resubstituting, I'm getting this equation. Similarly, putting equation 3 in 6, I get one more equation, and finally putting 6 in 8, I arrive at this equation. It's simple. And in matrix form, I convert it, I get a state space representation of it, so that afterwards, when I'm simulating these parameters, I can write the program in my MATLAB, and I can utilize it to say the transfer function of the various devices. So this is the modeling, mathematical modeling of the ultra battery. Now, as far as the energy storage devices are concerned, why I am doing this and all that thing. So I have to see whether I will use a backup diesel generator during an energy outage, or can I use an ultra battery. So utilizing energy storage devices have two things. First thing is it will dampen the response, and the second thing is that it will make the system to reach steady state faster. So it will reduce the number of oscillations, which will save us the economics and the power lately. And now the aims and approach here would be to, first of all, how to integrate this unit to a normal power system. So energy storage unit in an AC as well as requires a power conditioning system. So we have utilized the voltage converter, voltage source converter. It's a 6 pulse with modulated PDM. It incorporates a 2 quadrant DC DC chopper combination, and it has a DC interlink capacitor. So synchronous operation of VCS takes place within the network, wherein DC DC chopper, basically, the by varying this duty ratio here of the chopper, we are managing whether energy needs to be released to the system or needs to be stored within the ultra battery. So this integration of this chopper is this is the mechanism. Here I have my ultra battery fixed over here. So this is my 2 quadrant arrangement of the chopper, and my this is the DC interlink capacitor here. So this represents my VCS, and this is my PWM, and this is the from the AC side, and this combination is from the DC side. So this is the power conversion system I am using. So I am able to control my magnitude and voltage angle through converter terminals. Both real and reactive power can be controlled independently in this mechanism. I am interested to control the active power mechanism. So here the converter operation is basically begun with the blockage of IGBT gating signals at the beginning through charging of the DC link capacitor over here via the diodes. So the diodes are here, D1 and D2 diodes are here. So VSC keeps uniform DC link voltage. Transfer of power by ultra battery is equivalently represented in circuit enclosed. So this is how the transfer of power happens. So this is my ultra battery mechanism. Here is my rates, switching state from 0 to 1. So if my duty ratio is greater than 0.5, so basically my mechanism is 2D minus 1. If it is greater than 0.5, so it must be zero point 0.6. So 2 into zero point 0.6 would be 1.2. 1.2 minus 1 would be 0.2. 1.2 minus 1 would be 1.2 minus 1 would be zero point 0.2. So at this stage, it would be a charging mechanism. Similarly, for discharging, if you have like less than 0.5, it's zero point 0.4. So it's 2 into zero point 0.4, 0.8. 0.8 minus 1 would be minus 0.2. So in that case, it starts to discharge. Whereas the ultra battery would remain standstill if you are writing 2 into zero point 0.5. That is 1 minus 1. It will not neither charge nor discharge. So essentially, this is the mechanism for this thing. So I have incorporated the ultra battery into the power system, and I have seen the responses of the power system. I have introduced a step load disturbance at time interval 0 second, and another back-to-back disturbances I have given to see the robustness of the ultra battery at 0 seconds, because a time period is of 60 seconds one cycle. So after every 60 seconds, like for 0 seconds, 60 seconds, 120 seconds, and sorry, 0 seconds, 60 seconds, 100 seconds, and 160 seconds, I have seen between 60 to 40 seconds have applied a disturbance. So when I'm applying a disturbance representing a load outage by a step function, which I have taken in per unit value 0.01 per unit I have taken. So I notice the red line representing the step disturbance outage, without the inclusion of the ultra battery. The moment I have included the ultra battery, you can see the deviation is significantly reduced with the blue line. And as far as the oscillations are concerned, see the number of oscillations with the red line are tremendous number of oscillations. And even the oscillations are reaching the steady state equilibrium position very lately. But herein you see the smoothness and the peak overshoots are lesser. Here it is almost near to 0.06, here it is less than 0.01 or almost to 0.01. Similarly, this is for the two areas of the power system with the inclusion of ultra battery. And now we will see the what happens to the tie power deviations with ultra battery inclusion. Same thing, if you see the red graph, what we have done is with the inclusion of the ultra battery, the red graph is with the step load disturbance without incorporation of any device. But when we are incorporating the ultra battery, the deviations get reduced and the smoothness and the power system reaches steady state very faster. So this is what was needed for with ultra battery. So in a power system, what happens is that a rise in electrical power output of the machine was observed for a brief period to correlate the quick acting primary response in encapsulating inertia and governor action. What happens in a power system normally, there is a synchronous energy stored within the synchronous system, that is the synchronous generator, that is the rotating mass. So essentially when there is a disturbance or a small load outage, this mass acts and provides the electrical energy, but for a short period of time, and it reaches a different equilibrium. But if you don't have any energy storage element involved in it, then finally you have to go for load shedding purposes. But if you have a smooth electrical energy storage element connected to it, you can go for a longer period without the load shutdown, and you will not encounter much oscillations, and that in the longer run would leave you to less power like loss, because there is a lot tremendous amount of energy consumed by shutting down and starting the system. And this will help from the consumer side as well for providing the reliability of the system. So the fast acting battery is helpful in providing frequency regulation services. So a conventional three area or a two area power system model was developed. Incorporating, we have incorporated the governor deadband and generation reheat constant to give a pragmatic approach. Ultra battery was utilized for load leveling and active power control. Discharge of energy storage in the event of contingencies was seen. And these are the references what I have taken. Thank you very much. Any questions?
Thank you, sir.
Thank you. Thank you, sir. Any question?
Thank you, sir.
Thank you, ma'am.
Thank you, sir.
Thank you. Any questions, sir? Arjit sir, any questions?